Good afternoon, everyone. Thank you for joining us today. We're going to jump right into this briefing. We're starting a few minutes late. We appreciate you coming, and we appreciate all of those who were able to join us online. My name is Mace. I am the Deputy Director of the California Council on Science and Technology. I'm going to give you just a little bit of an overview about our organization and the process, and then I'm going to turn it over to our study team to dive into the findings of this report. So, as you know, the California Council on Science and Technology was requested to produce a study looking at the minimum heating value and maximum Siloxane specifications for the delivery of biomethane to public gas pipelines. And so you're going to hear in detail some of the findings from that study. The full report is available online to you, and we're happy to have this briefing that will also be recorded and available on our website. I also want to thank Assemblymember Holden, who helped co-sponsor this briefing for us. So the California Council on Science and Technology is a nonprofit that was created 30 years ago at the request of the California Legislature to provide an impartial, independent source of science to inform decision-making for the state. And we've been serving in this role ever since through a really powerful partnership with a whole network of experts. And this network is really such an incredible wealth for the state, and having an entity like the California Council on Science and Technology that can tap into it is really important so that we can help make the connections between all of the knowledge that's being created, all the investment and research that's happening in California, making sure that that information can be leveraged to inform the work that you do as decision makers. So we're very proud of this partnership. We're proud of the opportunity that CCST can have to provide across-the-board connections through all these universities and national laboratories, and we are happy to take on questions that you may have. So if you have topics that you think would benefit from this type of expertise, we'd be happy to talk to you about it afterwards. So what we do when we have a request from the legislature or from one of our agency partners is we tap into that network that I just displayed, and we convene a study team of experts, and we convene a steering committee, and we convene authors, and we develop and apply a rigorous process to each report. It's very important that what we deliver to the state can withstand the scrutiny that it will receive, because this is really important that all of the findings be useful to inform possible proceedings in the future. And we do that by not only having a crack team of scientists and engineers that we engage in the process, we also have a very rigorous conflict of interest evaluation process and peer review process so that we make sure that what we deliver is useful to you. And with that, I'm going to turn it over to Professor Jim Sweeney, who is the chair of the California Council on Science and Technology and also the chair of the steering committee for this study. But before I do, I just want to take one moment to acknowledge Dr. Sarah Brady. Can you raise your hand, Sarah? Who was the lead for this on CCST staff and has done a lot of the heavy lifting and coordinating on this. And so if you're engaging with us here in Sacramento and you have questions about this study, she can help direct you to the answers and to the experts. With that, great. Professor Sweeney.
Thank you, Amber, and thank you all for coming. You can read the list of the steering committee members. It represented people with expertise from the national labs, from private sector, from academia, and it was our responsibility to provide some oversight and to take the real work that was done by Adam and his team and really make sure we had a consensus on the conclusions and recommendations. So Adam Brandt, Gregory Von Wald were the key people that were doing most of the work and will give most of the presentation here, with assistance from Deepak Rajagopal and Austin Stanian. The assessment was based upon a combination, the peer-reviewed literature, the available data from the various agencies here, and then expertise of the of the overall steering committee and the expert and the researchers doing it. We really focused on 5 different areas. The first was the minimum heating values, and as you know, that we now have regulations about what the heating value, BTUs per standard cubic feet of natural gas going into pipelines. And the question is, should that be, should the biomethane at a lower heating value, a little bit lower, be put into it? Second, the siloxane concentrations, and Adam talked you more about siloxanes, but those are much more of a challenge than we envisioned at this time. We'll talk about the cost implications, and then we've said, in fact, although you might want to put natural gas in pipelines, there's other ways you can use it. You can use it to generate electricity, for example, not just the natural gas, I mean the biomethane or the biogas. And the question is, why was it all going into transportation rather than some of the other alternatives that look like they may be more economically attractive? And we'll spend some time talking about the regulatory distortions, the market distortions that came from a combination of a stacking between financial incentives at the federal level and at the state level. You will do not have time to read these recommendations. We'll come back to them at the end, but there'll be 8 recommendations that Adam will be developing as we move along.
Thank you, Jim. So, and thanks, Amber, for the introduction. So I'm Adam Brandt. I'll run through a few of the key portions of the study, and then hand it back to Jim to talk a little bit about economics. So, how are natural gas and biomethane similar or different? Raw biogas can be collected from landfills, wastewater treatment plants, or produced intentionally in what are typically anaerobic digesters processing dairy waste, food waste, or agricultural waste. This raw biogas typically has a high CO2 concentration, other trace constituents or contaminants, and has to be upgraded to produce what's typically called biomethane or high purity biogas. Biogas from wastewater and landfills faces a particular challenge in that it contains silicon-containing compounds such as siloxanes, which are not naturally occurring but which are added to various consumer products and therefore can end up in biogas associated with these 2 sources. After the upgrading process is complete, that is the removal of CO2 and other trace contaminants, upgraded biomethane is typically a very close substitute for natural gas. It can be blended into the natural gas system. An important difference, though, is this last piece here, is that biomethane lacks some of the heavier or higher molecular weight hydrocarbons that are present in natural gas. So, for example, natural gas is primarily methane, 1 carbon, but also contains ethane and propane, for example, containing 2 and 3 carbons. Because of this lack of higher molecular weight hydrocarbons, biomethane tends to have a lower heating value, which is something that we're going to talk about at some length. There's a variety of regulations affecting biomethane, and in particular affect the pipeline blending of biomethane. These include gas quality specifications, health protective constituents, and pipeline integrity constituents. Pipeline quality specifications are basically a variety of, gas quality specifications are a variety of rules around the gas composition and quality. A key one being the minimum heating value for injection into the pipeline, which we discussed, reviewed, and commented on in some detail. There's a variety of health protective constituents and issues of concern that have been addressed in prior reports from OEHA and other state agencies, so we don't really tackle those here. But we do talk a lot about one particular issue affecting equipment integrity, and this is siloxane concentration, which are these silicon-containing compounds. So we really focus on these 2 bold areas. That's not all the issues affecting biomethane, but these are the ones that we'll talk about. Okay. So let's start talking about heating value specification. So heating value is regulated around the world in pipeline systems to ensure safe combustion and reliable heat delivery of gas. That is, you want the consumer receiving the gas at the end of the pipe, whether it be a home, an industrial facility, or a business, to receive the amount of heat from the gas that they're expecting to receive. The current regulations in California are twofold. In so-called Rule 30 regions, including SoCal Gas and San Diego urban regions, require a numerical value of 990 British thermal units per standard cubic feet, and that's the numerical measure. In Rule 21 regions, or PG&E Northern California regions, broadly conceived, the standard is instead consistent with historical standards for the given receipt point, and that can actually vary by region within a PG&E district. One of the challenges with this numerical value of 990 BTU per scuff is this tends to be highly constraining on the allowable biomethane composition and make the creation of the biomethane more challenging and more costly. Okay. One important sort of impetus for this study was the idea that shifting the minimum heating value specification to a level closer to 970 would actually allow for improved adoption of biomethane and lower cost due to the somewhat easier process to produce 970 BTU. Heating value is one aspect of what might be called gas interchangeability. Gas interchangeability is basically the set of factors or the suite of factors associated with switching or blending gases of different compositions. So interchangeability is not just a biomethane issue, but for example could arise if you're blending and switching to a hydrogen pipeline system in the future. Heating value is one aspect of interchangeability, but not the only one. So for example, this is a diagram inspired by some work by the NGC Plus working group, which was a working group of industry experts convened to look at interchangeability. And they say that you may have some complementary index such as heating value and then an index that they recommend called the WOBE number. The WOBE number can be thought of as heating value. It has the same units in BTU per standard cubic foot. So it's like the heating value, but slightly more useful. We'll talk about that. At high WOBE number, you can have problems like carbon monoxide formation from incomplete combustion, NOx, or what's called yellow tipping. At low WOBE number, you'll have flame lifting carbon monoxide on the other side due to lack of combustion constituents or even flame blowout. Okay, so this is the lower energy content level, the higher energy content level. And they recommend, what NGC Plus recommends is that there's a viable operating range of WOBE numbers, and that is in fact what they recommend as the useful regulatory constraint on the energy content factors associated with interchangeability. How WOBE number differs slightly from heating value, and what it measures is the rate of energy delivered through a fixed orifice at a constant pressure, which is typically how gas is consumed in home heaters, appliances, dryers, ovens, and things like this. At low WOBE, which is the concern with low heating value regulations, incomplete combustion and carbon monoxide, resulting in carbon monoxide and possible blowout are the concerns. We can run a model and say, I'm going to assume the biomethane is a mixture of methane, CO2, and nitrogen. These are the bulk constituents in an upgraded biogas or a biomethane. And we can ask what fractions of CO2 and nitrogen are allowed given various specifications. We can see here, for example, in a Rule 30 region with a 990 BTU per scuff limit, the red region is off limits for one or more of the regulations. The white region is feasible. The important thing to note here is that the feasible region allowed by the 990 BTU per scuff limit is constraining on the amount of nitrogen and carbon dioxide allowed. Whereas if, for example, a minimum WOBE number was used in combination with a 4% max inerts concentration limit, you would actually open up a wide range of compositions. And would allow basically compositions with higher nitrogen, where am I missing it here? Higher nitrogen or higher carbon dioxide, which are easier to produce, lower cost. Okay. We believe that the evidence suggests keeping the current minimum WOBE number specification but that relaxing the heating value standard to a level near 970 is unlikely to impact safety or equipment reliability. There are many heating value levels near 970 that satisfy all Wilby number requirements according to NGC plus safety regulations around Wilby number deviation from historical averages. 970 is extremely common. California had a 970 specification until 2006, and it's by far the most common specification in North America. We see no issue with equipment or otherwise associated with the 970 specification. On the other hand, a 950 specification or a level near 950 would violate NGC Plus's recommendations about deviation in Wilby number from historical values, and so could potentially affect safety. And so we would be not recommending lowering the heating value specification to levels that low. Recommendations: so one, keep the Wilby number requirement as it is now, and examine regulations on heating value with an eye towards relaxing the heating value specification while maintaining safety via Wilby number, but allowing heating value values near 970 BTUs per standard cubic foot. Okay, so the next piece is on siloxane concentrations. So siloxane, these are these silicon-containing compounds. They're found in a lot of lotions, creams, shampoos, and other consumer products. Siloxane contains silicon. Silicon, when oxidized, makes silica, SiO2, which basically can be thought of as sand or sandy or glassy material. Significant evidence exists in the literature of silica buildup and failure of combustion devices utilizing gas with siloxanes. This usually results from deposition of this sandy or glassy material onto nozzles, heat exchanger surfaces, or in combustion orifices. The current regulations in California are 0.1 milligrams of silicon per cubic meter. This current specification is based on extrapolation from a study of 1 or 2 appliances and is not robustly supported by science. Significant operational experience with siloxanes exists. That is, there are many biomethane facilities that the gas does contain siloxanes, and they have been utilizing the gas. But unfortunately, the lack of data associated with these projects does not make it a very useful evidence for the safety or lack thereof of a given siloxane concentration, and we'll talk about that. There's little systematic study here. This makes it not very useful. We heard very poor disagreement between different kinds of parties in communication with experts on the measurement capabilities of different laboratories that measure siloxane. And so we'll talk about the sort of evolving state of siloxane measurement. In general, we think there's weak evidence for loosening the specification, just like there's weak evidence for the current specification. We don't see strong evidence that actually loosening it is a good idea because there's not much evidence in either direction. And there are, of course, concerns with risk due to an overly tight specification. This is one of the reasons why siloxanes were studied in this report. So what kind of operational experiences are there? This is a Coalition for Renewable Natural Gas maintains a database of existing projects all over the country, or actually Canada and the United States. There are 47 total operational landfills that send gas into pipeline systems, and 11 operational wastewater treatment plants in a whole variety of states. So these are projects where the gas is currently being used, okay, where there's potential siloxane contamination. This is a piece of evidence that the gas is currently being used. However, it's not useful evidence for one standard or another, because actually it's unclear what compositions or qualities this gas is actually being used at. That is, we know that these projects are using the gas. There's been so little systematic study that we don't know if that's a data point in favor or against California's standard. It's not really a data point yet in favor of a particular numerical standard, and we'll talk about what would be needed to get there. But it is being used. It's not like this is not being done. Potential health impacts of siloxane are poorly studied. We do know that the silica size distribution of siloxane particles, these little grains of material that are formed during combustion, through study at USC, combustion scientists found a size distribution peaking at about 100 nanometers. This is about 25x smaller than PM2.5. This silica nanoparticulate is amorphous in nature, not crystalline. So the larger health impact associated with silica exposure is typically seen to be from crystalline silica, which is very disruptive to cellular processes, and less thought to be associated with amorphous or blob like structure rather than a crystalline structure. Far more study has been done to date on crystalline silica. Exposure is going to depend on how much deposition occurs within the appliance or equipment that's burning the gas versus how much ends up in the air. At typical siloxane concentrations at or near the California standard, we don't expect exposure to people to be anywhere near OSHA or other regulatory requirements, because these are small amounts. So this does not meet levels near what is regulated for silica exposure in workplaces and things like this. Even if, for example, all the combustion products were not vented but were instead brought into the house, you're still not going to exceed OSHA-like recommendations. Summary here, not well studied. They're small particles. They're amorphous, which are less well studied. We don't think we're going to have large mass or particle counts from combustion. We were hearing lots of different opinions about siloxane measurement and standards. This was interesting. So biomethane advocates have claimed in a variety of publications that the current siloxane specification is below reliable detection limits. We also heard this from other industry observers. This has, they claim, made it difficult to acquire project financing because of risk associated with regulatory shut-in in a world where you are not meeting the siloxane specification, or you are meeting the siloxane specification, either one, but the measurement is problematic enough to make compliance with the regulation uncertain. Utilities, on the other hand, maintain that they do have a lab that they can use, and in particular SoCalGas has permitted the Point Loma wastewater treatment plant to inject into the Southern California gas system at this level, and provided us with test results showing Point Loma compliance below 0.1 milligrams of silica per cubic meter. Okay, so we're hearing different things. We hear from SoCalGas that it can be met, and in fact they've already approved Point Loma. We hear from biomethane providers that there's uncertainty around measurement. This uncertainty around measurement is actually well known. ASTM International, which is a standards body, kind of like ISO or one of these other standards bodies, has currently had a multi-year process underway to document standardized and regularized siloxane measurement methodologies. This is underway. Hopefully it will be wrapping up in the next few years, what we hear from ASTM affiliated folks in this process, but it is underway. So hopefully, the hope is that this process will convene a standard set of measurements and measurement protocols, so that siloxane measurement will become a more certain thing. Current California siloxane specifications of 0.1 are based on very little data and involve large extrapolation from the data. This is not necessarily a critique of the California regulatory process, more of a statement about the state of the science and how much is known. There are just very few studies out there. At present, there is no standardized measurement protocol, such as via an ISO or ASTM-like process, that would allow dependable measurement of this level. However, several testing laboratories, including those used by SoCalGas, claim to be able to measure this amount. We haven't been able to independently test these claims, and really one of these standards bodies is the right sort of body to adjudicate measurement accuracy claims. There's not enough information in the scientific literature right now to know whether 0.1 is too stringent or not stringent enough. And so it's very hard to make a recommendation to tighten or loosen that standard. Some sources are very unlikely to have siloxanes, such, for example, as dairies or digestion of agricultural waste. We don't expect cows to be using lotion or shampoo. So we believe that a very reasonable thing in this world of, where we think we know where this stuff is coming from would be that sources that aren't expected to have siloxanes could be held to a reduced or simplified verification regime to eliminate the costs associated with measurement and verification of something that we have no reason to expect to be in the gas. And then we do suggest that there needs to be additional testing and experimentation. So recommendations. Keep the current siloxane standards as an interim standard. We do not see scientific evidence to either increase or decrease these. We support a comprehensive research program to understand operational health and other consequences. We recommend considering developing a reduced and simplified verification regime that doesn't unduly penalize dairies and other siloxane-free sources, okay, that might hinder their development, because this is important for the industry. We recommend that monitor the ASTM process so that when a standardized test protocol arrives, it can be used and adopted in California. And revisit these siloxane standards once more information is available. Okay, let's see here. So we also analyzed the implications of the regulation for cost and value of biomethane. We looked at the impact of the heating value specification, the impact of the siloxane specification, and the regulatory or financial incentives for biomethane development. Our colleagues at UCLA, Deepak Rajagopal and Austin Stanian, his graduate student, performed a survey. 28 biomethane upgrading companies were contacted. They received 7 complete responses, including system designs and costs for upgrading systems. And you can see here that the red are the costs to meet 990 per million BTU, and the green are the costs for the same kind of facility to meet 970. And so we see an increase in cost between 50 cents to $5 in order to meet a 990 versus a 970 standard. This is another piece of evidence in favor of relaxing the heating value standard to a level near 970 to allow lower cost biomethane to be developed with no safety implications. Siloxane removal, the economics of that were studied in detail in a GTI 2014 report. And to give you an indication, at the Point Loma wastewater treatment plant, that cost is perhaps $2 per million BTU. We performed in the report a variety of regional modeling case studies. And so you can see here zip code level gas quality simulations for situations where, for example, this is January, April, July, and October of 2016. We took historical consumption values and modeled, basically built out in this case of 100% of the biomethane facilities that were in a database compiled by UC Davis as part of a CEC project. And you can see here we can model in some cases, for example, in the spring, a depression in heating value at some regional nodes associated with injection of large volumes of biomethane. And so we do have some simulation kind of case studies for you guys to look at in the main report showing these sort of geographically resolved results. Jim's now going to talk about alternatives to pipeline injection of gas.
The biggest focus of, oops, okay, what did I do? Okay, the biggest focus of the study has been on putting the biomethane into a natural gas pipeline. But the reality is biogases are first produced, whether we have it from agriculture, from wastewater treatment, or from any of the other sources. That can generally be used directly for heating or for electricity, either on site or for short dedicated pipelines. We can have an upgrading at a significant cost, and if you saw the cost graph, say maybe in the range of between $5 and $15 per million per million BTU. I want to remind you that this product replaces natural gas, who has a market value of $3. So we're paying in the order of about $5 to $15 to upgrade it to have a product that is worth $3 at the end. And when it's upgraded, oops.
It's the top one.
It's the top one's a laser. When it's upgraded into biomethane, it can be again used directly for heat and electricity, or be put into the pipeline. And the question is, if you look at all these projects, most all of them create the biomethane and put them into the pipeline to be used in vehicles, to be used primarily in vehicles which are natural gas vehicles. And you've got to convert the vehicles to natural gas, and you put this biomethane into a pipeline, and it commingles with the natural gas, and so there's a contract to get the natural gas. The question is why that is all going on when it looks like many of the other alternatives would be economically attractive as opposed to it. It's important to understand that any way you use the biomethane, it substitutes for natural gas almost any way you do it, whether it's directly for heating, for generating electricity, or for transportation purposes. And the environmental impacts of it for carbon dioxide releases are approximately the same any other ways you use it. So there's not a big environmental payoff for putting it in a pipeline rather than directly electricity. So now there's some projects that stop releases of methane into the atmosphere, particularly the agricultural products. Just avoid projects, avoid biomethane being released. The value to the environment is high for reducing the methane, but that value is the same whether it's used for electricity or or for transportation. There's absolutely no difference. So why is this happening? Well, it's interesting to look at the incentives that are created by the state low carbon fuel standard program and the federal renewable fuel standard program. If we use the biomass, upgrade it to methane, put it in transport in pipelines, and a certified pathway, the state will give a subsidy between $6 and $48 per million BTU. Remember, the city gate value of the product is about $3 per million BTU. So we'll get, state gives us $6 to $48. The $48 is when you're avoiding methane releases, and that's the state values at in the order of $125 per ton of carbon dioxide or carbon dioxide equivalent, and it's based upon the market there. Federal renewable fuel standards gives you $29 subsidy, and they add together, so that the subsidy that you get for this product, if you use it in transportation, is $35 to $77 subsidy for these products. By the way, some of them are in California, but the majority of them are in Texas, Ohio, Canada, around the United States. And so the federal subsidy is going through all of those. The state subsidy is going to Texas, Ohio, Canada, and so forth. If on the other hand, you take that biogas or biomethane used for residential, commercial, industrial electricity generation under the current regulatory systems, you get about $1 worth of cap and trade credits at the California level, 0 federal renewable fuel standards for a total benefit of $1. If you use the biomethane to generate electricity and you connect that electricity directly to charging stations, or some other way you can certify it's used for transportation, then you get the same subsidies in California. You get half the subsidies at the renewable fuel standards, and so you still get a $21 to $63 subsidy. So that answers the question: why do we have this massive market bias away from using it for electricity, where generating electricity in many cases, maybe the more economical way of doing it. Generating electricity can be just as environmentally attractive as doing it for the carbon dioxide, but we have federal and state regulations that were basically separately put together. How much time do I have?
Approaching 2 minutes.
Okay. When California passed the renewable fuel standards, excuse me, the low carbon fuel standard, they knew the federal government had a renewable fuel standards. At that time, at the federal level, these projects were eligible to get advanced biofuel, what's called RINs, Renewable Information Numbers, and the value of those were maybe 40 or 50 cents per RIN, giving you a value of $5. At the federal level, there's also a requirement that there's cellulosic ethanol as part of the renewable fuel standard. That technology hasn't changed. So a few years ago, the federal government redefined biofuels into cellulosic, although it's nothing to do with cellulosic, it's redefined it. And they get RIN values of $2.50 each, and that's why we get that 29. So the federal massive subsidies happen after the California set their rules, and then the federal setting their rules usually don't pay attention to what California does, and so we have these stacking on one on top of the other. So very massive subsidies away from using electricity and more towards biofuels. So a conclusion is, it's an important question for the state. How should you use the biomethane of the biogas? Should it all just go for transportation, and where it doesn't cause vehicles to become compressed natural gas vehicles? It's just substitutes for natural gas there. And we believe that the differential treatment under the federal renewable fuel standard and the CARB regulations create a substantial market distortion away from using this biomethane for electricity and towards natural gas. Therefore, a recommendation: state and federal agencies should examine whether the substantial differences in incentives for various uses of biogas and biomethane are consistent with the actual intent of the state and federal policies, or was this effect that is really inconsistent with the state's intention, and the state maybe should revisit how they operate their regulations. Let me turn this back to Adam.
All right. Okay, so I'll just conclude briefly with a few remarks summarizing these three sort of key pieces here. On heating value, we recommend investigation of options to relax the standard from the current 990 BTU per standard cubic foot towards a level near 970 BTU per standard cubic foot. Not recommending that exact value, but a level near that value, because that should not pose operational safety or reliability hazards, while saving fairly significantly on upgrading cost and equipment requirements. On siloxanes, we think the current standard is not robustly supported, so more research and data are needed before we can scientifically recommend relaxing or tightening the standard. We do have some recommendations to allow investment in the meantime, such as relaxed compliance for dairies, food, and agricultural waste digesters, as well as a little more transparency and clarity from Southern California Gas on the process by which the Point Loma facility was permitted, just to clear up some of this question about measurement of this standard. And then third, the current specifications affecting biomethane, affecting volumes of biomethane by affecting basically the costs of meeting the standards and compliance uncertainty associated with, for example, the Siloxane regulation. I will just put up the recommendations again. These will stay up here while we take some questions from the audience.
Any questions? Yes, Amy.
Hi, thank you for that presentation. I think you're talking about operational issues that can arise from the siloxane, not just health impacts. So I was wondering if you could talk more about that and the mechanism by which siloxane can cause operational problems.
Can you repeat the question for those? Who are
Yeah, so for those on the phone, the question is discuss a little bit more the causes of operational difficulties associated with siloxane containing gas. Yeah, so we can talk a little bit more about that. So siloxanes it's a whole family of compounds. There's many of these. They have different properties, and so certain ones are used in certain applications. But in general, they contain silicon bonded to hydrogen and oxygen. When that is oxidized, the silicon breaks free and is fully oxidized. Its thermodynamically favorable state is to become silica or SiO2, silicon dioxide. SiO2, that's silica is sand, beach sand, is mostly silica. Okay, so this silica is formed, the way it's actually formed due to high combustion temperatures is it's molten. And so what you have essentially is small particles of melted sand, rock, or some people call it glassy. Depending on the other constituents, it'll be more sand-like or more glass-like. This is molten. It's flying through the exhaust products post-combustion. For example, leaving out the stack of your natural gas water heater. This then, as it cools, it'll hit metal surfaces, for example, deposit and harden. And this builds up in a variety of places. It can build up in heat exchangers, flues, or exhaust vents. Limit airflow through this equipment and therefore cause combustion difficulties. It can also deposit quite problematically on sensors. Silica is an insulating material both thermally and electrically, and so it will deposit on sensors, for example, sensors that detect whether or not a piece of equipment is working properly. And so you'll have silica deposit on this sensor and you'll have sensor failure. That was a common thing seen in the literature. This has been tested and empirically shown a number of times in combustion labs where equipment does fail. And in fact, the current regulation is based on an extrapolation of some failures seen in natural gas burning equipment in these sort of laboratory combustion tests. And so basically what they did is they ran the equipment on a gas containing a relatively high concentration of siloxane compared to what is currently regulated. Recorded the time to failure, how many hours of burning did that require, and then use that number to essentially extrapolate down. If we set the standard at 0.1, for example, what's the effective number of hours that the system could operate before it fails? And they based the 0.1 standard on extrapolating to a 15-year equipment life. And so the idea behind this standard is fine. It's saying we want to set the standards such that the equipment will not fail in a 15-year operating life, which I think is a fine way to think about it. It's just based on very few measurements on very few pieces of equipment, and so it's not clear how robust the evidence is for that standard. So we can't recommend it's too tight, therefore loosen it. Neither can we recommend tightening it. We think there's just too little information out there, and therefore recommend more study.
Julia, go ahead.
Yeah, and then
Yeah, I want to start by thanking Adam and Jim and the other authors, and also Amber and Sarah. This is so important to help move this industry forward in California. You haven't mentioned dilution in the pipeline, and I'm surprised, especially for the siloxanes issue. Wouldn't dilution in the pipeline be a factor one way or another?
Yes. So we do have a chapter on dilution. It didn't make it into the key report, or these key recommendations. Dilution is an option in some cases, but is not seen in the scientific literature as a reliable or robust mechanism. So the idea behind dilution is I have gas containing, let's say, not 0.1, but 0.3 or 0.5 milligrams of silica per cubic meter. I don't meet the specification, but for example, I may be blending a relatively small volume of this biomethane into a pipe that carries much more gas. So the effective concentration seen by any party downstream or by a party downstream could be much smaller and in fact could meet the standard. And so the idea behind dilution is you don't necessarily meet the standard at the point of injection, but you meet the standard for anyone who's using the gas, and therefore, and that's why we have these standards, right, is the folks using the gas. So that's the logic behind dilution. It makes a lot of sense in some cases. The problem is, depending on, and this is one of the reasons we did these flow simulations, depending on the relative volumes of gas injected at a pipeline node versus the gas consumed, you can get a whole host of different things going on. So if the amount of biomethane blended at a location is relatively small compared to the amount of gas flowing through the pipe, you will have dilution, and this is seen, empirically and via modeling over the scale of sort of a few hundred meters. So that shouldn't be necessarily a big issue. If, on the other hand, the volume of biomethane that's being injected is large compared to the flow in that region of the pipe, what you'll instead have happen is what they call slugging. So you'll get basically sort of slugs or plugs of relatively unmixed gas flowing through the pipe, and then folks can see this high concentration downstream. Or you can get actually complete displacement from a local node or a local region of the natural gas, and the biomethane can effectively completely displace. And so what we recommend about dilution is that it's not a general solution to this problem. It could be feasible locally in some locations, but it can't reliably be relied upon, particularly in regions. We did a case study in Hanford. Our case studies were the Bay Area, San Diego, and Hanford. And in some of these more rural regions, the amount of biomethane producible is quite large, and the amount of gas consumption is small. And in these kinds of regions, relying on dilution to meet either a heating value or a siloxane standard, we don't believe is feasible. And so we don't recommend it as a general solution to the problem, although we do recognize that it could be useful in some situations. It's kind of where we come down in the report. I think we had here.
Yeah, so I just wanted to kind of follow up on the dilution question, because we've seen in certain regions, depending on what the market is for ethane or pentane, some gas processors will just be dumping a large amount of ethane into the pipeline, so you actually get a pipe that has a lot of hot gas, where the dilution would actually be very helpful.
Yep.
So in the coming up with your 970 BTU, were all of those factors considered, in terms of what the concentration of heavy hydrocarbons currently in the pipeline and what this dilution might actually achieve?
Yeah, so the concentration of and expected heating value coming down the pipe will vary as a function of market conditions, usually over scales of kind of years to decades as new natural gas plays come on board, commodities markets shift. And so what will happen is the value of these higher molecular weight hydrocarbons, ethane and propane, they'll shift with secondary markets, plastics, petrochemicals, and things like this. When those products are less valuable, the producers are incentivized to put it into the pipe as much as possible. When they're valuable, they're more inclined to strip them off and sell them. And so you'll see these fluctuations usually over time periods of kind of multiple years, where the gas will get hotter and less hot depending on which gas is coming in, which fields are coming on, and what the economic value of the pieces is. You're right, in the case of if you had a hot gas coming down, then the dilution would actually be a valuable feature of biomethane. Similarly to the other dilution story, we can't rely on that as a reliable mechanism for sort of compliance. You can't expect that, for example, if gas is coming hot right now, that it'll be coming hot in 6 months or 5 years. And so we don't recommend relying on dilution for the same reason as a general solution to this problem. There can be lots of cases where it could be useful, but we can't recommend using it in general. And in particular, the smaller the fraction that the biomethane is going to be in a particular region of the system, or the particular pipe that it's being injected into, the more viable dilution is going to be. The more end system branch versus trunk sort of scale, the further you're injecting it towards the ends of the pipe, where flow is less, consumption is less, the less opportunity there is for dilution. So it really is kind of this case-by-case basis, is what I'd say.
Earlier there was mention of rocket construction because of the different subsidies and the policies for state and federal. Do we know the size of that market distortion for like a rough order of magnitude?
We know the dollar value of it. It's the dollar values that I put up on the chart. What we do is, if you look through all of the projects that have been set up, you see that most of them are transportation related. Very few of them are electricity. And yet you also know that there's various technologies that could have been used to generate the electricity in a very clean way, either fuel cell technologies or there's some new non-combustion. A company called Adagen is doing that. And so we have those technologies. They look like they would be less costly, economically more attractive, and there's almost none of them happening, so that it seems to be a very large effect. But what we can measure is, because we can't measure what would have happened if we had a level playing field. We can measure how on level the playing field, and those were the numbers I put up, massively on level.
In the way back, yeah.
I'm wondering if you clarify whether diverted organic waste digested at the wastewater treatment facilities, or faces the Siloxane issue, or if you would recommend that that's eligible for the relaxed standard.
So our understanding is that what in some portions of our report. Oh yeah, sorry. The question was, what about diverted organic material, for example, co-digested with wastewater sludge or other kinds of materials, and how would that fare under this reduced verification standard for siloxane? From the evidence we've been able to see, segregated municipal solid waste organics, food processing residues or agricultural residues are also not expected to see siloxane. There's no real reason to expect that. There's no natural process by which they're formed. They're purely man-made compounds, and so we don't expect them to be on people's yard clippings or these other sources. Whereas landfills, which can contain appreciable quantities of siloxane or wastewater due to volatilization of stuff that's essentially washed off our bodies down the drain. And so what would happen if you were co-digesting with a wastewater derived or organic material, you would get in the situation where what would be expected to be siloxane free, like an MSW or a green waste diversion to a compost, that would then essentially be commingled with something that could contain siloxane. And so that would be an issue associated with kind of co-digestion, would be that you wouldn't want to mix sources that would be not expected to produce siloxane with sources that would be expected to produce siloxane. Now, that's not saying that wastewater treatment plants can't meet the standard. According to SoCalGas, we do discuss this in the report. The Point Loma facility does meet the standard and is injecting today into the Southern California system. And so this is not that wastewater treatment plants can't meet the standard, but that I wouldn't recommend a reduced verification regime for a system that was co-digesting ag waste or MSW diverted organics with wastewater residuals. Just because you're again doing this mixing or sort of contamination.
We have about 1 minute, so super quick response.
So yeah, I just wanted to mention you referenced the 47 active landfill facilities from the RNGC data.
Yeah.
I was wondering, did you take a look at the siloxane levels in those landfill gas facilities? Since a lot of those have been running some close to 10 years now, if there's been any adverse effects from them injecting gas into the local systems and any end-use application?
Yeah, so we do discuss this at length. That's what we're calling our operational experience. Clear, there's a ton of projects operating that have been injecting gas. Greg and the other graduate student did reach out. We had some personal communication with operators suggesting that there hadn't been experience of any sort of challenges. No systematic study has been done around these landfills to see if any issues have been arisen or go out and measure deposition on local water heaters and things like that. So no systematic approach, just largely anecdotal. The other challenge with using that information to say California should set or loosen a standard is that it's not clear what those facilities are actually sending onto the system. So there is was it a GTI study that had samples pre and post cleanout for a variety of landfills, but that's essentially the only study. So we don't have any studies that, for example, match landfills with the post cleanup gas composition with the impacts downstream. So what would be really nice and a really pretty straightforward follow-on study would be to say, let's go to these facilities and actually take some samples. Then once we've taken some samples, go and visit some facilities, start asking in a more systematic way if there's been any issues. associated with this, so that you could actually use that operating experience in a more robust way. Right now, what it says is, well, there's been a bunch of projects operating, but still little is known about how they're operating, what they're actually putting onto the system. That is not actually that good of evidence either way. It's just an evidence. It's sort of anecdotal and not systematic. But we think it's actually reasonably straightforward to make a systematic data set out of these operating projects. It just needs to be done.
All right, well, I want to thank all of you for joining us. For those of you online who are able to join us, I want to thank our study team. I know they might be able to stay for a few minutes if you have some specific questions. Again, the full report is online. This presentation will be online. For those of you who RSVP'd, we do have some lunches for you on your way out. And we do ask you to fill out a survey for us. Please let us know what worked well, what we can do in the future, what other topics you'd like to hear about. Thank you so much for joining us.